Session. Uh, Today's session is titled Sustainable Arctic Seas, AI and Environmental Protection. And today's session is jointly organized by Arctic Frontiers and KMI. Through this joint seminar, we seek to share AI technology and Arctic research between non-Arctic and Arctic regions. It's my great pleasure to introduce today's chair, Anu Fredriksson, Executive Director of Arctic Frontiers. Please give a warm welcome and applause to Ms. Anu Fredriksson. Thank you.
Thank you, Dambi, and good afternoon, everyone. We live in the middle of times of disruption, and AI is one of the greatest ones. Welcome to today's seminar organized by KMI and Arctic Frontiers, focusing on Arctic seas, the use of AI, and environmental protection. As was said, my name is Anu Fredriksson, and I'm the Executive Director of Arctic Frontiers, which is an Arctic organization based in Tromsø, Arctic Norway. It is a partnership including the largest Norwegian organizations and businesses working in and with Arctic issues. And this partnership wants to promote knowledge-based development of the Arctic. Now, before we start the discussions, I am pleased and honored to welcome a friend of the Arctic and Deputy President of Korea Maritime Institute, Dr. Min-Soo Kim. Dr. Kim, the stage is yours.
Yes, thank you for introducing me. I hope you enjoyed all sessions for the Arctic Partners Week and this session as well. Yes, I prepare a very short comment for my... good afternoon. It is my great pleasure to welcome all of you to today's seminar, jointly organized by the Korea Maritime Institute and Arctic Frontiers. I would like to express my sincere gratitude to Ms. Anu Fredriksson, Executive Director of Arctic Frontiers, for her invaluable contribution in preparing this meaningful event and for her significant role in enriching the overall program of Arctic Partnership Week. As we are all aware, the world is grappling with the profound impact of climate change, and the Arctic is at the very center of the global challenge. The transformation of oceans and glaciers in the Arctic highlights the urgency of addressing these changes. Against this backdrop, advancement in blue technologies driven by AI and smart technologies hold great promise for preserving a sustainable Arctic and marine environment. In particular, for Arctic communities characterized by sparse population and remoteness, innovations such as automations, unmanned systems, and smart technologies are indispensable for driving sustainable development. Moreover, eco-friendly technologies have the potential to minimize negative impacts on the Arctic Ocean, safeguard its fragile ecosystems, and unlock the region's best potential, ultimately serving as the foundation for sustainable growth in the Arctic. In this context, non-Arctic nations like Korea, with its expertise in smart technologies in the shipbuilding and maritime sectors, have a unique opportunity to contribute to the Arctic through collaborative efforts. Given these pressing challenges, today's session, which focuses on sustainable Arctic seas through the lens of AI, smart technologies, and environmental protection, could not be more timely. I hope that the insights and discussion shared by our distinguished expert will pave the way for innovative solutions to achieve a more sustainable Arctic and Arctic Ocean. Korea remains committed to contributing to the Arctic future, driven by a shared vision for sustainability and cooperation. Together, we can build the Arctic future we all aspire to achieve. Thank you.
Thank you, Dr. Kim. Now I'd like to invite all the participants on stage for a photo before we get started with the discussions. Now, to set the stage for the discussion, but also to provide you a glimpse of what Arctic Frontiers is about, we would like to show you a short video related to Arctic Frontiers 2024 and the discussion we had about the use of artificial intelligence in the Arctic.
We have enough challenges if we're going to solve some of the problems. We need the new materials that you can only create through AI. We need to be able to analyze data in new ways. If we look at the Arctic, it's often a hostile environment. We need the autonomy that's going to be able to help us understand that and get the data sets that we need.
The most common way to think about AI and sustainability and climate change is to think about it as pieces of a puzzle of Lego. So you have one thing, an energy system, and then you think about, so how can I add AI to that to optimize something?
We need to know what's happening with the sea level rise, for example, related to the melting of the ice caps. We need to look into the future, and I think that AI can help us to do that.
Arctic AI, or any application of AI for the planet, we need to start thinking about how do we move away or complement the current focus on prediction, optimization, and efficiency that is so dominant in this space to something that focuses more on co-development and uses of AI that support local solutions to people that matter. If we're clever enough and we're intelligent enough, we can use these tools to not only adapt to climate change and transform out of climate change, we can use it to listen to what nature has to say.
So, can we use the AI to listen to what the nature has to say? That's the challenge for our first speaker, Executive Secretary of the Arctic Council AMAT Working Group, Rolf Rødven, an Arctic expert originally from the northmost part of Norway, Tana. He leads the Arctic Council work on monitoring and assessing the state of the Arctic region with respect to pollution and climate change issues, as well as their impact on both ecosystems and human health. Dr. Rødven, the stage is yours.
Clicker? Okay, so. Thank you so much, and thank you for inviting me to this very exciting session for something that will transform the way we look on the Arctic as well as on science in the future to come. I will in my talk speak a bit about the background for why AI may be a good tool to use in the Arctic, about the complexities of the Arctic, about how it has been used, and about some of the challenges by using AI. Okay, let's skip this. So AMAP has, since the very beginning, been focusing on monitoring and assessing both contaminants and climate change, how they affect ecosystems, how they interact, and also including how they affect people living in the Arctic, including human health. That in itself is a complex mandate to have, but it is even more complex if you look into the area where we're going to deal with this. So we're talking about the Arctic, and what is it about the Arctic? Well, the Arctic is not a homogeneous environment. The Arctic is differing, both depending on the different Arctic states, different on abiotic processes taking place when it comes to sea currents, air currents, and so on. It differs when it comes to biotic features like ecotopes, food webs, and ecosystem interactions. And that adds a complexity to it, which makes it a bit challenging to deal with it as a one homogeneous whole. Also, as I like to remind people about, particularly when we run outside of the Arctic is not a nature reserve. It contains people. People of different ethnicity, people with different knowledge system, people with different background. Well, more than 9% of them are from 40 different ethnical groups. Most of the populations live in very sparse areas, and a lot of those settlements are located on permafrost, which also does add into the local use of AI. So the Arctic itself has processes that complicates the understanding of the pathway from the origin to the result. When it comes to contaminants, most of the contaminants originate from outside of the Arctic, and they are amplified throughout the system. So it's not a one-to-one ratio on the pressure and the response. Similar when it comes to climate change. Climate change is happening 3 times as fast in the Arctic as anywhere else. And this is doing so because of what we call is Arctic amplification. So again, that means that 1 unit of greenhouse gas emitted in somewhere has a different response outside of the Arctic compared to inside the Arctic. And this kind of this kind of feedback, amplified feedback, makes it more complex to understand the process going on. How will the response be? In addition, these 2 major processes interact. So, for instance, when it comes to contamination levels, it's not only affected by the sources of contamination and the pathways itself, but it's also now amplified by climate change. Climate change is now remobilizing contaminants being deposited on glaciers and sea ice. It is releasing, for instance, metal mercury from permafrost thawing, and it's increasing the flux between sea and between sea and air, which again increases the uptake of contaminants in the food webs, and again, you do not have a linear response. So even though that the sources for contaminations have been regulated and you see a decrease in the emissions, we now see a flattening out and even an increase in the response or in the uptake in the food web. The ecosystem itself is for us a kind of a black box when it comes to climate change to understand. We know the abiotic processes quite well, not perfectly, but quite well. But when you add on the ecosystem on top of it, it's much harder to understand. Does the change in the ecosystem state amplify or dampen climate change? 2 examples of that could be, like for instance, an increased amount of algae due to warming could increase the CO2 uptake, and then, of course, decrease the climate change. Likewise, increased thickets wood that sticks through the snow in winter decreases the albedo and amplifies the warming. So it can work both ways. So this is an extra layer of complexity that makes it difficult to understand how climate change will affect the future of the Arctic. And some of these processes are non-linear. And I would remind us that of those, what we call tipping points, that is non-linear processes which may have an irreversible effect, half of those exist in the Arctic. And you can see them on the map from these two papers on the left-hand side and right-hand side, showing that, for instance, sea ice disappearance, the Atlantic circulation, wildfires, and so on, are such non-linear, irreversible processes which are very, very hard to model. By definition, because we haven't been there before. So, how to move forward then? Well, one way we have, oh sorry, there was supposed to be a movie there, but it didn't start. One way we are moving forward when it comes to monitoring is by autonomous monitoring systems, like drones, for instance. Drones can help us to monitor places which are remote and hard to get. And I was hoping I could run the movie because it would show how we can monitor glacier dynamics on Tunabren. It allows us to do sampling in areas that are hard to get into, in times that is hard to be there, for instance, in winter and darkness, and in areas that are also risky for us, and to avoid disturbing the area while doing the monitoring. One example of that is, for instance, on the deep sea. When we speak to our climate experts, they say that one of the major questions we have is how is the processes in the sea going to affect climate warming, global warming, and we don't know. But one way of doing so is to use automatic drones or underwater drones or gliders to measure temperature, salinity, and currents in places we've never been before. And you can do it all through the year and on a low cost. For instance, by this excellent vehicle you see on the lower right hand here. It's called Boatimac Boatface, and it's the autonomous underwater drone from the British Antarctic Service research vessel. Also, as I said, the Arctic is inhabited, so we do have a lot of knowledge there already through indigenous knowledge. And this knowledge is not quantified in numbers, but is qualitative data through language, through expressions, and through stories. That is very hard to model under a conventional modeling framework. But you can do so by using AI, by combining those qualitative data with quantitative data, combining meteorological parameters with expressions for snow under different conditions. So what is the way ahead? Well, when we talk about machine learning, this is one of my favorite equations. When we talk about machine learning, we think of it as something new. This equation is also about learning, but it's from 1763 by a guy called Thomas Bayes. It's called the Bayes theorem. So these two little orcs, they discuss, and they say, like, we need to find a better way to find fish. What if we just search for where we find other birds? So what is the probability of finding fish, given that there are birds there? Well, to do that, you need to know what is the probability of finding fish, and what is the probability of it being fish there, what is the probability of being birds there, and what is the probabilities of it being birds, given that there are fish. And those kind of conditional probabilities you can update with your data. And that is actually the basic of machine learning. So even though we think about it as a modern invention, it has been there for a long time, but we just haven't had the computational resources to deal with it. So where do we use AI now? Well, we've seen that AI has a tremendous potential when it comes to methodology. sorry for the misspelling here. The DeepMind AI by Google are now outcompeting our traditional weather forecasting, using actually less computational power. Also this year, Microsoft's AI was the first one to do a global air pollution model. And also I should mention the Climate Trace project, where they're able to, by using AI, to combine top-down monitoring with bottom-up monitoring of emissions, where you're actually able to pinpoint and estimate emissions of greenhouse gases on a global basis. By using AI, you can have precise forecasting. It's not so computational exhaustive, and you have the potential to access both quantitative and qualitative data. However, it's rather data exhaustive. Also, just as other methods we have, it uses retrospective data. That means that we are trying to predict the future by using the past, and that may have its challenges. And also, one problem is that it contains some black boxes. Like, we do not know all the, it's very hard to run the diagnostics when you do not really know what's happening in a model. So to be able to make sure that we have the best model, we need to make sure that we could do the right diagnostics. What we are looking into now also is what we call digital twins. Digital twins is a set of AI systems running simultaneously. So you do simultaneous simulations in a system, and that allows that kind of complex interactions. For instance, we are now running digital twins on CIS Dynamics, and I know this will be presented more on later. We do see potential on using digital twins for weathering couplings on high-altitude weather systems with low-latitude weather systems. Sorry, high-latitude weather systems with low-latitude weather systems. And also to look into what I presented earlier, the ecosystem modeling of climate impacts. And also inclusion of indigenous knowledge. And again, we need to find ways of, as we do in our more traditional modeling, like the CMIP modeling, to exchange processes for comparison. But again, I would say that digital twins is a way forward. Yeah. But it's not a holy grail. So, and by that, I say thank you with this picture of a jumping polar bear. Thanks.
Thank you so much, Rolf Rødven. Now, our next speaker represents the Norwegian Polar Institute, which is one of the leading global institutions working on both poles, and also a senior partner at Arctic Frontiers. Dr. Tore Hattemann serves as the section leader for oceanography, and he has worked on various issues related to oceanographic processes, both in Antarctica and in Arctic. And the Norwegian Polar Institute has been tasked by the Norwegian government to make a new marine protected area plan for the Arctic. And similar process is already being conducted in the Antarctic. And Dr. Hattemann will present the work done in the Antarctic to us. Dr. Hattemann, the stage is yours.
Thank you very much for giving me the opportunity, inviting me. It's a pleasure to be here, and it's quite an exciting event and venue. So just a quick comment on the introduction. The NPI has not been tasked to make an MPA proposal for the Arctic, because that is more complicated than just doing the science for it. But we have been tasked, and we'll come back to that, to transfer what we've done in the process of making a proposal for an MPA in the Antarctic, use the same methodology to assess area-based management possibilities for the Arctic. Slight change. Anyways, let's dive into that. That's why I want to showcase this Antarctic part. And just to give you a bit of a background, this is on the other side of the globe, but a lot of people at COPRI at least know the Antarctic quite well as well. In the Antarctic, the ocean is sort of managed by the Commission for the Conservation of Antarctic Marine Living Resources, CCAMLR. It's an international body, and they do consensus decisions. And here is a map of suggested marine protected area regions, and the one on, unfortunately, I can't show the pointer. On the very top of the figure, there's Phase 2 Weddell Sea MPA proposal. That's the area that we in Norway have been working at to suggest a way to manage this, and that should be done by having a specific planning area with defined conservation objective associated with conservation features and targets, and potential costs and benefits for existing projected human use and in the planning area. And based on that, we made a prioritization exercise. All these steps have been done without any AI, but I think they are perfect examples of how AI may help us with those actions in the future. And this is also the methodology that we've used here, is sort of the blueprint of what we're now trying to look into the Arctic. And to break this down into smaller pieces, how this has happened, how we have done that, first, there was a big exercise on data collection, harmonization. We have created an online atlas of different features. And this would be, for example, an input data set that you could use on an AI method. We have done the traditional spatial planning prioritization approach after that, not using AI, but just doing an optimization algorithm, applying that to these data. And then, as a third step, we also tried to sort of improved existing methodology by putting in some new considerations about what happens if the climate is changing and what happens if the world is not just static. Yeah, just another little background coming from the Norway region. This is a little map of parts of the Arctic that shows you the size of this area for which we've done that. The difference, this is only a small part of the Arctic, so it might seem like a small area, but if you live in this area, you know that from Norway to Iceland is quite far, and this area of ocean is quite large. And our big challenge in this exercise was that in this entire area, we have like maybe 3 vessels passing through per year, and maybe one of them doing a little bit of science and monitoring. So this is a vastly understudied area where we have a lot of data gaps, which we had to deal with. Still, we need to create this input data, and this is then an example of this atlas of the harmonized data sets that we made of all these different features. Here are features shown of some geological, geomorphology properties, vessel accessibility, which is mainly determined by sea ice extent, and the toothfish or Antarctic krill habitats, which are the potentially to be deployed species, as well as like other things like top predators and lower trophic species and physical properties of the ocean, the currents. This is all part of this atlas that we created. And then there was a working group that defined all these conservation objectives. You don't need to go through them in detail, but all of those translate to making sure that some of these features are undisturbed when the rational use, which is shown on the right side, the potential fishing and the vessel accessibility is put in place, so that there can be an equation for how to optimize this. And based on these input data, we then created an online app, a website basically, where you can set your targets and select which kind of rational use you want to include. And on the lower left on this website, you see like a few of these features that would be included. And then this can be run interactively by the user to sort of define or create scenarios for conservation purposes. And the picture, the map with the 2 blue shadings, shows you sort of an output where like some of the areas selected to be part of the conservation area and parts are not selected. And the whole purpose of developing this tool was that, going back to that KMI convention, it should be an international agreement around things, so people should be able to transparently see how this plays out and design their own approaches to that. This is now a fairly static approach. It does not take into account time dimension, seasonality, but that's something that can be incorporated. But this was really our approach to make this sort of a democratic tool for people to discuss different scenarios before any suggestions would be made. Now, coming a bit more to my work, which is on the innovation side, what I was concerned about is that traditionally those feature maps are static maps which are localized, but knowing the ocean dynamics, things are dynamic, things are connected across the domain. So we spent a bit of thought of how to include this dynamic connectivity aspect. Like traditionally you have these maps of habitats, but if you ask an ocean model, this is how transport looks like. If you release something, for example, krill larvae, that will not stay in the area that you're concerned of, but it will go to other areas, and the area itself will also be affected by other areas, and there may be stepping stones. So based on this kind of work, simulations, we created additional features which give us an indication of where things come from, where things go to, and also where things get stuck in our planning area. And we can define metrics of important through-flow areas and important retention areas, which were the layers that I showed you before that were then included in the prioritization exercise. This work has also spun off some more like process understanding things. You can look at the different krill populations around the entire Antarctic and see how they are connected. You can see how the ocean is breaking up in, just from its dynamic point in the lower right of the picture, like different dynamical areas and how those then are interlinked. You can do lots of network analysis on that. And this is not using any AI, but you could feed this into some AI that then helps you for a dynamic assessment of systems for the Arctic. Yeah, this is just one last example. In such a modeling world, you can also look how things are transported if you only consider the ocean, or if you consider drift of larvae with the sea ice. And as you see on these two movies, the upper and the lower one, that gives a quite profound difference. And we're still not sure what's the right way of prescribing this, because as Rolf said, we understand the physics quite well, but as soon as you start to look into the ecosystems, there are so many open questions that are still a challenge. And the second innovation part that was also mentioned is we need to consider not only today's situation, but we need to look into the future. So this was an approach, and that's mainly developed by the University of Queensland, which was working a lot together with us in Australia, how to consider climate change or defining a climate velocity and take that into account, which regions are supposed to be more stable in our prioritization and which regions are we expected to change. So what I said initially, this was the case study for the Antarctic, and now after delivering this to the Norwegian government, they said, well, can't you do something similar for the Arctic just so that we have a tool? And there is currently an application to PAME about such a project where we want basically to copy this approach, not for making an MPA proposal, but simply to have a tool for area-based management in the Arctic. And yeah, this will happen over the next few years, led by NPI with collaborators from Canada and Kingdom of Denmark, and as well as open for feedback with other experts. So that's it.
Thank you very much, Dr. Hattermann. Now it is my distinguished pleasure to introduce our third speaker, who is a postdoctoral researcher, Claire Ayres from COPRI, a good collaborator of Arctic Frontiers throughout the years. Her research focuses on ice, ocean and atmosphere, And she has also expertise which stretches both poles. Claire, the stage is yours.
Thanks very much. So today I wanted to come and talk to you a little bit about how we're starting to use AI approaches for sea ice prediction. Now, sea ice prediction is an emerging area, a topic of research here in South Korea for two reasons. One is operational. So we've had a lot of problems recently getting to bases in Antarctica, but also just understanding how to manage sea ice at field stations, but also because it's a really important component of the climate system. And those are two very different timescales that you're looking at sea ice on. And I've just got a little figure at the bottom there just to show you how important sea ice is. So you can see the 2024 sea ice cover and how much that's reduced since the average from 1981 to 2010. And in the red, I've got like a projected 2030 cover. And so it's becoming increasingly important that we model sea ice. So why is it important? Well, albedo. So sea ice reflects albedo back, sea ice reflects sunlight back. But it's really important for deep water formation and global circulation. And one thing I wanted to show you is the effect on ecosystems. So in this plot here, I've got the coverage of global coral reefs at the bottom, the Amazon rainforest, and then the summer and winter ice extent for Antarctica and the Arctic. And you can see that we've got a huge amount of area is covered by sea ice. And we realize now that there's a very important biogeochemical process in sea ice that is important for feeding animals underneath the ice, which then is important for food webs. And so there's cascading changes, if the sea ice cover changes, on those food webs that we're still really just beginning to understand. It's also, as we heard earlier in the shipping discussion, becoming increasingly important. Shipping routes are opening up. But as with everything, it's not as simple as less sea ice, easier shipping routes. So we've got changing sea ice types. So the ice is becoming thinner. It's drifting around a bit more. So some shipping areas are actually becoming more dangerous because of different type of ice. So we really need to understand where is the ice so that we can safely operate in these regions. So this is my brief, very incomplete history of sea ice prediction. So we really started to want to understand sea ice in 2007, when we had a really, really low Arctic sea ice. Hit the news, scientists were very worried, and that sort of catalyzed this sea ice prediction network to come into place. So this is a network where scientists get together and share their models and try and work out how we can better predict sea ice. In 2017, SIP and South came online, so this is modeling sea ice in Antarctica. And in 2019, there was actually a workshop where they discussed where is the future of sea ice modeling going. And in that workshop, there was no mention of AI. So it wasn't on the agenda, no one really discussed it. We had a sea ice modeling workshop in Korea in October 2023, and every single presentation mentioned AI or machine learning techniques. So there's been a real explosion of approaches and how people are using these approaches to model sea ice. And in this talk, I really want to just show you how that's happening. It's kind of also coincided with the explosion of AI techniques in weather forecasting. The sea ice community is a little bit behind the atmospheric community in terms of their modeling. They're embracing of machine learning techniques, but as I'm going to show you, I think it can help at every single stage in the sea ice workflow. So traditionally, when we're trying to model sea ice, we start with the observations, and those observations can inform the physics parameterizations. We use observations to validate models, to bias correct the models. We assimilate observations into the models. And what I want to show you today is I'm going to give you two examples of part of those sea ice workflow that AI can contribute to. But also, we're starting to develop AI models of sea ice themselves. So AI can actually also model sea ice. I'm going to talk a little bit later about maybe why we don't necessarily want to do that. So this is an example here of NextSim, which is a sea ice model that models rheology. So it models how ice deforms and how it flows with different stresses. And so this is a physics-based model. But some of the parameters are difficult to constrain. So within this model, they have these two parameters, we'll just say C and P, these two parameters that they're looking for, and they don't know what those values are. So these are two parameters the model needs to take in order to represent what the ice looks like. And traditionally, they use trial and error to try and work out what those parameters would be. So Anton Karasov and his colleagues at the Nansen Center, they applied deep learning technique to try lots and lots of different parameters and constrain what was the best way to tune them to, so that they can get the most realistic patterns that match, so from radar sat, so from satellite. So the exciting thing here is that we're using AI techniques to rapidly constrain parameters that we struggled to constrain before. So although the AI is not modeling something that's physically realistic, it's finding physically realistic parameters that can then go into the sea ice model. A second example I wanted to share with you was bias corrections. I'll just start off by explaining the difference between, so a sea ice model on the left, we traditionally break up each grid cell into multiple thickness distributions, and there's snow on top of the sea ice, and we might have an open water fraction, and that's actually a very good representation of reality. But actually in the reanalyses data sets, they tend to just use ice or no ice, and they have a constant thickness. So in the example there, I've just shown you like GERA55 and ERA5, they're the two most common reanalysis data sets that we use. GERA5 has just 2 meters, so if there's sea ice in their grid cell, it's 2 meters thick. ERA5, if there's sea ice in their grid cell, it's 1.5 meters thick. And this has a problem with the data sets that you're going to use. And bear in mind that for AI techniques, we tend to use gridded data sets. So this is the data that we're putting into the models. And so the implication of that, so on the left, I've got an example of if your real-world ice is thicker, it's going to affect the conductivity through the ice. So you're getting less conductivity through the ice. So your reanalysis has got a positive surface temperature bias. And conversely, the other way around, if you've got thinner real-world ice, then the conductivity is changed again, so you've got a negative surface bias. And so if you're going to use that data, you're going to have to bias correct it. You'll have to tune your model because the data going into it has got a problem. So one of my colleagues, Lorenzo Zampieri, who's now working at ECMWF, so he did this really interesting piece of work where they decided to use machine learning, so they used a neural network to bias correct the reanalysis data before it went into their model. So they used some data that's not in the reanalyses, so to look at temperature, and they picked 4 predictors, so 2 atmospheric, surface temperature and downward long-range radiation, and 2 sea ice predictors, so thickness, sea ice thickness and snow thickness. And they fed that into their neural network and came up with the difference between how these changed and the model, and came up with something that they could tune the data set with. And when they did that with the ERA5 skin temperature, then they got a 27% average reduction in the errors. So by applying this before you use the data set in your model, you're now eliminating the need to do some tuning. I'm really running out of time. So what I wanted to briefly just touch upon is some of the challenges and considerations. So we can discuss this hopefully a bit more in the discussion section. But one of the main things is that we train our AI systems on observations, and so they're going to inherit any of the defects that are in that. So we also train AI on model outputs as well. So we need to make sure that we know what the uncertainties are in the data sets that we're using. And one question that I have is, do we have enough independent, long enough sample data sets to train machine learning for sea ice applications? I'd argue in Antarctica we definitely don't, perhaps not even in the Arctic. Tuning is crucial, so we need the right expertise. Machine learning techniques, it's a huge field that's been developed. It hasn't been developed specifically for sea ice applications, so I think that we need to make sure that we have computer scientists on our research teams to help make sure that we're using the algorithms correctly, to make sure that we're refining them towards what we want to do. Another thing that I think is really important is physical understanding. We need to make sure that we can trust the information that we're getting out. So that doesn't mean I don't think you can use machine learning. I think you can. I just think you need to make sure you understand what you're doing with it. It's very, very important that if we're using AI for prediction, that we can interpret our result and it is trustworthy. I just wanted to just give you a little bit of a heads up on a new project that is coming up. So the WMO has got a new group called PCAPS, so Polar Coupled Analysis and Prediction for Services. And as part of that, I'm setting up a task team that is going to look at AI CIS models and try and improve their trustworthiness. So what data sets do we need to be able to use those systems, and how do we incorporate them in a way, how do we validate them in a way that they can be used by people who need to use them in the Arctic? So can a ship's captain trust my AI prediction of where the sea ice is going to be? Another thing that we want to also do is try and bring in more data sets, so bring in all of the really rich data sources that we collect that don't traditionally go into reanalysis data. So the Mosaic expedition was several months of data was collected on sea ice. That doesn't traditionally go into reanalysis models. Is there a way that we can use them in AI models? So that's something we really want to look into. So with that, I'll wrap up. So I think AI has a really important role to play throughout the sea ice modeling pipeline. It can speed up parameterizations. It can help us bias correct data. It can help us put data into the models. We can even use AI to run models. And some of the SIP and South, so the Southern Hemisphere sea ice models that run now, the most successful ones are not the physical models, they're the statistical models. I think we've got a long way to go on development of AI in terms of sea ice modeling compared to the atmospheric models. And I really think that quality data to train the models on is absolutely important. But I think it's a very exciting area of research. And I think it's something that perhaps if you're doing anything related to sea ice, really consider, can you use machine learning algorithms to improve what you're doing? Thank you very much.
Thank you so much, Claire. Now, unfortunately, we have just received the word that Professor Wong-Suk Choi from National Korea Maritime and Ocean University is not able to join us due to an emergency. And we, of course, send him our warmest thoughts. So we will move straight to the panel discussion part. Just give the crew a few minutes so that they can set the stage, and we will continue. Thank you. So thank you so much to the staff for setting the stage for us, and thank you to our presenters for great remarks from different perspectives. Now, I'd like to start with an open question to all of you, but perhaps inspired by what we heard you say, Rolf, about the need to understand the Arctic, the need to understand ecosystems, climate change, ocean processes. Is there something that we could learn from other places that could be also applicable in the Arctic?
I guess when it comes to AI in general, if I'm allowed to start, of course the major development is happening outside of the Arctic, the technological development, and then a lot of those, I mean the underlying technology is applicable there as well. However, you need to adapt that to those processes that we have identified. So it's not, I mean, we're not moving into a novel area, but it's about, taking time to understand technology, understand those processes, and understand to develop them in the best sense. And if there's anything we have learned from any kind of development of tools, is that there is no holy grail. There's no magic wand that you can just, whisk around and you will have the correct answer. You really need to understand the process. You need to understand the limitations, and you need to understand the possibilities when you want to apply it to the real world. Thanks.
Thank you. Tore.
Yeah. There was an example on the screen for how things from other regions can be transferred and learned. So I'm not going to repeat that, but maybe on the methodological level, what was an important realization for me when we did this exercise in the South was that it is really crucial to be aware of, when talking about conservation or management, what the objectives are and how those project on the features that are included in your system. And as long as you're not fully aware of that, and for this Southern Ocean example, it really came down to that we need to assign values to what is the loss of not allowing krill fisheries in this area, versus what is the loss of harming that and that population. So you really need to be able to quantify what your values are. And this, in a large and inhomogeneous area as the Arctic, is probably the largest challenge that will be faced in such an exercise, to do this consistently.
Thank you. Claire.
Yeah, thanks. I would say the other thing to add to that is there is a lot we can learn from other places, but we need the data in the right place. So one of the challenging things for the Arctic is we increasingly have more data. So people often say, well, we've collected a lot of data, is that enough? But there's two reasons why I think we need to really look at that. Is it in the right place? It's very hard to collect data underneath ice. Technologies are improving, so we need to really focus on where are we not collecting data and how can we collect it? And I think that's where new technologies can really help. But then the second thing is also, I was going to say the second thing. Yeah, so where is data, but then how are we then using that data? And I think there's a lot of data that maybe isn't currently being used enough. So I think we need to set up better ways of how to share that better.
Thank you. Now, Claire, you especially very well kind of outlined the use of AI, or where we are in the path so far. And we've seen that it's already been taken in use in the Arctic Ocean and in sea ice monitoring and analysis. But if we think about the use of AI in the Arctic going forward, where do you see the biggest potential? And again, an open question to all of you. So Haller, if you feel like you'd like to start.
Yeah, so the biggest potential, I guess, is initially, I think, being able to speed up processes that we have. So one of the challenges with models is sometimes they're very slow running, especially if the more processes you want to include and the more things you want to interconnect together. And being able to speed up parts of that process. So for example, cloud parameterizations are very slow to run. So maybe if you can take a part of your model and speed that up, that gives us much better, quicker running models, which is important for prediction. I mean, and so people need to have information now on so they can be in dangerous areas working and living and working. But I suppose long term, it's working out how how to make the best use of information that we have. It's very expensive to go. So I said we need data in all the places we need it. How are we actually going to be able to go under every single grid cell we need to get the information in? And so I would like to see that maybe AI could be used to help understand exactly where it is we need to collect information. And I think that could be make better use of when we go to certain places and how. And then finally, ideally, we want to not have to go there to collect data. So if there's a way that we can improve information from satellite and improve algorithms to try and make sure that we don't have to go in the first place, that would really help.
Thank you. Tore, please.
Yes. So I was improving my own work, sitting in my hotel room this morning using AI to write computer code. I think that is a big impact that we're all feeling. There are two other perspectives I think that are relevant. One of them is the operationalization aspect, in particular thinking about planning, management, shipping, whatever. These are all dynamic systems, and we need something that is quickly adaptive to take into account new initial conditions, new boundary conditions, and adding data that comes in, like this Bayesian approach that Rolf highlighted. This is really powerful in AI, which once you have trained it, you can improve it and adapt it. This is more complicated with traditional deterministic models. The other component is that the danger of AI is it is a black box, but the strength of AI is it is a black box. We can actually use AI to connect multidisciplinary and really inhomogeneous questions, like with a graph neural network. You can suddenly connect shipping with physics and see connections once you have the training data. Coming back to, we need enough data, but once we have it, this is really useful, and then dynamically use it for the predictions. Yeah.
I would like to add on the two previous speakers here, and what you say is really important, like how to make the processes more effective when it comes to parameterization of those models and so on. And one thing I would like to point to is what I had up on the screen, the tipping points, where we do not really know what we're going into, because we never, I mean, by definition, all our empirical work is retrospective. So we do not know what is ahead of us, because those linear dynamics are quite complex. But we can use AI to simulate and make parameterization, which we can actually test, and maybe we can also identify which part of the process we can target data sampling for, and see how that insight can kind of bring us forward on understanding that. And as Tore also say, like, some of these processes are running so fast that it's, I mean, Arctic warming is taking place so fast that we're actually, the change is outspeeding our understanding of it sometimes. So it's really important for us to be as effective as possible, to optimize the way we work, and to be in time, and particularly when it comes to, let's say, like some of those processes that need an immediate response, like when it comes to safety and so on.
So speed, but also uncertainty have been mentioned. But then there was also, one of you alluded to this in your presentation, the concept of trust. How trustworthy are the AI predictions, and what does it take to get, for example, a captain on board a vessel to trust the CI's predictions or other AI predictions?
I'd say we don't know that yet, which is why we're setting up this task team to try and address that issue. I think trust, at the moment, people want to have a physical understanding of what it is that you're doing. So an AI prediction, they're maybe not going to trust yet. So I think what's going to be really important to give people trust is that we collect the right data, we have a good process of validating. So we need to understand, how do we validate an AI model properly? So in a physical model, we can collect all the parameters that the physical model is simulating. So we can check the fluxes, is it doing the right thing? Whereas with the AI model, we're taking in a few variables and we're putting one out, and we can't necessarily see all. So I think we need to really think about validating these models. I think that will be the key one to make sure that people can trust the models.
And a quick follow-up, just how long does it take to validate those models?
Well, again, I think we still need to really understand which variables do we need. ones do we need to be sure of? What should people, so if we just take the sea ice example, what variables should people be confident in that they can then say, right, I think the sea ice is here because these ones have, maybe I've got the thickness right and the drift is correct, so now you can have confidence that I know it's there. But I think we don't yet know that. We're really just a few years into this really exciting stage. I really hope that these techniques can be, but I think they're starting to be proven that they are useful. But yeah, we need to really tie down how can we make them trustworthy. And I think that's not just an answer for me, a scientist who's trying to use these models to answer. I think I need to work with social scientists as well to try and understand what is it that, like a ship captain, how can he have trust in this information that I'm giving him? So I think we really need to collaborate across science to social science to understand how you can make these things trustworthy.
Yeah, there's also, I completely agree, and there's also another aspect of not only bridging the gap between the scientists and the users, but AI itself is not a given thing. It's also a science that has been developed by people, and we're currently developing AI research centers which deliberately should look at quantifying the uncertainty of the AI and also getting a handle on how it had made its decision. And these are basic research questions that need to be addressed in the math department that develop the AI algorithms. And for that purpose, I, as an earth scientist, have to learn to speak to them, which is also not easy all the time.
Thank you. I'm glad to hear that the scientists struggle as well, because I, as a layperson or someone with background from policy and business, definitely sometimes struggle. Now over to you, Rolf.
I would just say, it depends on your definition of trust. If you by trust mean that we will have a technology which never fails, which always is 100% certain, there's one thing that history has told us is that you, in that case, you can never trust science because there's always exceptions from the rule. There's always, and it's, this thing of uncertainty, and that's also the thing of development of science. Otherwise, we never even moved into the theories of relativity and so on, because we do see that it's always things, always exceptions from the rule. However, if you talk about minimizing uncertainty and validating models, I think what you also hear, like to have a scientific approach to that, it's really a way of building trust. Trust is a subjective thing, but you can make confidence by validating models, by always testing them and improving them, as you say, and bring it into a framework where you kind of compare different ways of doing these kind of processes and make it better. And I think in that sense, it's all about technological development as we've seen it before. So at least within this kind of use.
Tore, please.
Yes, and this matter of trust is not a new challenge since AI is on the scene. In Norway, there are now legislations that if coastal structures, infrastructures built, those need to take into account expected sea level rise. And by chance, I got talking to this engineer who's making these projects, and he's like, I asked him, where do you take your numbers from? Yeah, that's the IPCC projections. And how can you trust those? I mean, I'm part of developing those, and I know how uncertain they are. So this is a challenge that we're facing. But the other aspect is also then there needs to be an assessment of how legally binding might these AI decisions be, and there needs to be a framework around that. So it's also touching the social sciences again.
Thank you. Claire, did you want to comment or? No, okay. I would like to open the floor for questions, if there are any. So please start thinking about those, and if you have any, raise your hand. I will be keeping an eye on you. But before we do that, I wanted to touch upon one issue that I feel is of importance, and that is, of course, the indigenous aspect, and especially the aspect of indigenous knowledge, traditional knowledge. How can that be incorporated into artificial intelligence, or can it?
I guess I'll start that one, and I'll leave the technical parts to Claire and then Tore here. But I think it has a very huge potential, because there's a lot of knowledge out there which has not really been recorded in a quantitative sense, but we know it's there, we know it's valid, and these systems give us the opportunity by learning to put together patterns where it's earlier been hard to put together patterns by equations or other methodologies. So I think there's a great potential there. However, I would also say that it has an ethical component to it, because it has this thing about intelligence property rights, and to make sure that the knowledge holders are also acknowledged for the derivatives of their knowledge, or what the products of their knowledge in this case. So, and to make sure also that when you do validation, that is also, they are also brought into the system of validating the processes, because you can't validate processes without taking the data or the sources of the data into account. So I would say it's a great potential. And then for the more technical parts, I hope Claire and Tore can enlighten us more.
Claire, would you like to go now?
Yeah, so I think this actually is a really good opportunity for us to evaluate what data we are bringing into models. So I mentioned briefly in my presentation that we tend to run AI on the reanalysis data sets because they're nicely gridded. But to be honest, most CIS modeling applications, we're using the nicely gridded data sets so that we can compare with the nicely gridded model output that we have. And we're not using enough of campaign data, for example. So I'll give an example from the Arctic. The Southern Ocean is one of the most understudied places in the world, but we do have campaigns that go there and learn a lot for process understanding. So these campaigns do give a lot of information about processes that we want to understand. But then that data isn't incorporated into models. People aren't using that to test the models because it's not necessarily in a useful format for them. It's a point, and they've got 20-kilometer grid, and they've only got 3 weeks of data, and the model's only got 3 time steps in that time. And so I think evaluating all kinds of data, including indigenous knowledge, this is a really good time to be doing that. We really need to know more about these regions, so the polar regions. As Rolf said, they're changing really fast, which makes prediction hard. Weather prediction has become very good because it's based on lots of years of knowledge, and it's starting to be more difficult to predict now because we're getting many more extreme events that are just not in the model history. And so I think this is why we need to bring in as much data of any type at all. It's a good time. I think AI is now giving us that impetus to really think about what data are we using and how we're going to incorporate it.
Thank you. Tore, would you like to comment?
Yeah, for me, this is from a technical perspective. It's a question about interfaces, and to build those interfaces, incorporate that knowledge, you first have to get people in the room together to talk and exchange thoughts, and then there's probably a lot to learn. Like people living in their backyard will know which fjord is never freezing, things like that. But it's a matter of translation, I think.
Go ahead, Rolf.
And there's already existing a lot of projects or several projects on that. We have, like from AMAP's side, we're running a project called CITE, Climate Impacts on Terrestrial Ecosystem, where reindeer herders are recording snow features, and you can combine that with meteorological data, and you can make pattern analysis, and you can also, because it's not only about the climate, but it's also the geography, the type of terrain, and so on. You have similar on the Canadian side with the SEAKI project, which focuses on sea ice and sea ice conditions, where it's also about for them on transportation and the safety of the sea ice. And you have something called the CLEO, the local ecological observatory, circumpolar local observatory, which you can kind of gain that kind of qualitative input, and you can combine it with other input, and you can run those models. So there's already a lot of data existing there that could be exploited for this kind of training for artificial intelligence.
Thank you. Now over to the audience. Any questions from here? All right. With Dambi on the second floor. Second row, sorry. And there's actually a microphone coming up to you. And perhaps we'll group 2 questions. So Dambi, if we can take you, and then behind you. Okay. Yeah.
Hi, my name is Danby from KMI. I'm also a lay person and a social scientist in an observer country. So all your researches and all your work is so amazing. But I come to wonder, what can a policymaker in an observer country help with your research? Is this question valid as well? Yeah, thank you.
Thank you. And we'll take the second question as well.
Thank you. My name is Sung-Yip Jung from CRISO. I have a simple question for the technology and the indigenous people's knowledge. And considering the CI's prediction, in that case, we need validation data like sequence of the ice and ice edge distribution. In that case, we need some indigenous people's knowledge and experience to measure the sequence of the ice. So my question is, do you have any collaboration between the indigenous people to validate the AI simulation model? So thank you.
Thank you. So 2 questions. What can policymakers in observer countries do to help? And then CI's predictions, whether there's any collaboration with Inuits. And again, well, we'll start with you, Rob.
I can try to answer the first question. In general, from our perspective, when we do our assessments, it's always based upon what we call policy-relevant questions. It's a bit what you said about this kind of training. So it's purpose-driven or it's question-driven. Like, what do you actually want out of it? So that is, in general, the way we run our processes is to define what kind of scientific questions are relevant for policy making, and that could be one way forward on, and that's not only for the Arctic states policymakers, but also general, because a lot of those issues we are facing in the Arctic do have their origin outside of the Arctic. So thanks.
Well, in response to the collaborations with Indigenous people for data sets, I actually don't work in the Arctic, so I can't give you very specific information, but I do know that those collaborations are starting to be built and developed, and we're now realizing how important that knowledge is to contribute. So yeah, I can't give you any specific examples, but yes, that work is happening.
Thank you. Tore, did you have anything you'd like to comment?
Yes. Maybe it's related to both questions, actually, because the second question, this is being started because the government funding calls request this nowadays as well, that this is part of the projects. And maybe that's an input for the observer states, that closing the loop, feeding back to their stakeholders what should be part of the policy and the requests. And then this comes into the funding calls, and then we have to do it.
Thank you. Now our time is up, but during this discussion, we have heard how artificial intelligence definitely can speed up processes, but we need multidisciplinarity because it is a black box, and definitely collaboration across the different sectors. And there's also an ethical aspect to it, especially when it comes to acknowledgement of indigenous knowledge, if that's being chosen to be shared. And we need to evaluate which data we wish to bring into the applications. With these concluding remarks, please join me in thanking the panel for their expertise.